One, you have the frequency. The frequency is one output, and that's the frequency where this eigenmode happens. The second one is the eigenmode itself, or the eigenshape, or however you would call that, is like the way the part deforms at that eigenfrequency. Hi guys, welcome to this video. Today we're gonna take a look at Module 3 of the Inspire course kit. So, Module 3 deals with normal or eigenfrequencies, normal modes. Basically, normal modes or eigenfrequencies are very important for dynamic considerations. The famous example always given is the one of a bridge, where a bridge is there and then either wind or maybe some soldiers marching over that bridge excite the bridge into motion and then it crumbles down. So eigenfrequencies deals with that kind of problem where a structure has some certain eigenfrequencies, frequencies where it will resonate with. And that means that if you excite the structure with this kind of frequency, the frequency will resonate and the shape will deform. And how to find those kind of frequencies and how to find those kind of motions, this is exactly what this problem is all about, or this module is all about. So basically, we have the matrix here again, and we see with modular analysis, we have the same thing as before, like the contouring. Yeah, then we have the frequencies, that's new, and then we have the geometric modification. Additionally to that, I would say we also touch a little bit on connectors in this model and also creating our own materials. All right, but without further ado, let's get started. I will just load in Inspire, and load in the provided model file, which is just a geometry. You will see that you don't have any material set and also no thickness is set. You can see that not really here, but you can see that by clicking here and see that the thickness is 0 millimeters. All right, following the instructions, the first thing to do is to generate a material. And because this is not a standard or default material to use, but it's a custom plastic, a generic ABS material, which we have to define first. Okay, so basically what we're doing is we click here on materials, and then we have my materials here. And I created it already, but let me just do it one more time. So you just click on the plus, and you don't really care about those kind of things. You just care about the Young's module, the Poisson ratio, and the density. So this is with linear static analysis, this is all you need. So generic ABS. So the Young's module is 2650 megapascals. Then the Poisson ratio is unitless and has a value of 0.4. And then here you have to be careful. The density is 1.038 to the power of -9 tons per cubic millimeters, but here we have kilograms, so we can say E-6 kilograms per. Am I right here? Tons? Let me think one second. So if I have to the power of -9, so very less tons per. Yeah, I think that should be right. Yeah, I think that's all right. Okay, so we have that. Excuse me. Okay, material is set, but the parts don't have the material assigned yet. So you switch over to parts and just switch that out to be the new generated generic ABS material. All right, still you see that there is no mass, right? 0.0 kilograms, and that has to do with the fact that neither of those two parts have a thickness assigned to it. And you can also see it's a sheet or it's a surface model. You can also see that with the icon here. So basically two ways to see that. But this is for sure something you need to fix before running the model. Okay, so basically you would just select the two parts and then set a thickness of 3.175 millimeters. By the way, to just make double sure that we entered the correct value, you can switch the unit system here to be MPa, because that has millimeters, tons, newtons, and seconds. And just to make 100% sure we have it right, you can see, alright, so it's 1.038 to the power of minus 9 tons per cubic millimeters was indeed correct. Okay, so basically we have that. The next thing to do is to generate the constraints for this model. But to be honest, you could also just run it like this and also get results for eigenfrequencies, because for the eigenfrequency analysis, you would not 100% need constraints. You would get some modes which don't have movements of parts relative to each other. So that would mean, for example, if you don't constrain anything, the parts just could move back and forth, and that's a rigid body mode. That means the part itself does not deform or deflect, there's no strain, no stress, but the part moves in a certain direction. You could have one mode in this direction, one mode in the other direction, and also something like a turning mode in another degree of freedom. So basically the most kind of rigid body motions, what you would be getting is 6 different degrees of freedom. But here we have the task to generate the boundary conditions before running the normal modes or eigenfrequency analysis, which then determines the eigenfrequencies for the constrained part. So you just imagine what this is. This is some sort of, I don't know what it really is, but just think of it that this is being mounted to a wall, or this the ceiling, and this is being mounted to a wall. And then if you have it like that, which frequencies would occur with the constraints in place. So that's what you are dealing with here. Okay, so let's do constraints. Pretty easy. We already did that with 2D and 3D analysis. So basically, you just click here, for example, and then you have a constraint. But here's a specialty. If you want to really let this constraint be free in rotating, because you have a surface part, then you would like to do something like this. You click on here. Well, here it gives you just 2 options, right? But you would maybe also want to have the other rotations free as well. Then you just click here to move that. I don't know why it's bringing me that pop-up, but that's all right. Just move it a millimeter outside. That's enough. And then if you click once more, you can see that you have now the full control and can set free the different rotations. This would mean the following. This line is constrained in every translation, so left, right, fore, back, and also up, down, but it is free to rotate in every direction. So it could rotate like this, and like this, whatever, you know what I mean. Okay, let's do the same thing with the other side. So once more, I click here, then I go to the move tool. I will move it 1 millimeter here. Then I say, all right. Then I will click once more and just click 3 times to let the constraint be free in those degrees of freedom. All right. So we have that. The next thing is the area here. And what we like to do is, if that is really mounted to a ceiling, we would like to let also the translation in Z and X direction, you can see it here, Z and X direction, to be free. So in order to do this, we have to do a connector. Same thing, by the way, is being done here, but you cannot see that. But basically, what is being done is that you have something like a connector. And connector come in 2 flavors. They come in flexible and in rigid flavor. So let's just create that. Some more. Okay, I think that's all right. And you see that it says flexible. So the difference between flexible and rigid is that if you do flexible, the points, not here, I will call that master, and that those are the slave points. The slave points, they can move to each other so relative to each other, and there's no constraint with it. With rigid, you say, like, if you just use the hand as an example, the fingers to each other cannot move. They have infinite stiffness, and that's not right for here. So flexible is the way to go. Okay, so we have a flexible connector here, and then we can constrain the point here. That's the master node. And for sure we have to also let the rotations happen here. But additionally to the rotations, we would also like to have this thing happen. So those translation X and Z shall be free. Now, see that? It's also showing that to you like with a visual icon. See, there's a little ball here. It's like a ball bearing. So it's like it can move like on a circle or on a ball. All right, so that's the constraints, and I think there's no force, right? So there's no force, and we can run that now. So by clicking on here, pressing run, I think let's make it the same as with the instructions, 3.9696 millimeters. That should be that, and let's call that also constraint, because I also did a model with 3, so I will do that. And you see that here with normal modes, you can say, all right, how many modes would you want? And the instructions tell you to go with 10. That's all right for here, but in industry, make sure that you have enough modes. And just as a little tangent here, the way how you get enough modes is by just setting a bigger number, but basically a way to see that you have selected enough modes is to sum up all the percentage of effective mass, which is the output you could get, but not with, I don't think, with Inspire. But you have the complete mass and the effective mass. And if the effective mass, that means all the parts that is moving in the eigenfrequency spectrum, if that's close to each other, then it's all right. So then you have selected enough modes. But that's another topic. We could go and a whole lecture into this, but we won't do this here. And I think that's all right. For now, the only thing the instructions here tell us to do is use first order elements. That's just to make it a little bit faster, and then let's just run it. Make sure that you are in the OptiStruct run profile. This will not work with SimSolid Solver as, first of all, I think the connectors is a problem, but 100% the surface part is a problem. SimSolid can only work with 3D parts and not with the 2D part like we have here. Okay, I'm not 100% sure how much time this will take, but it could take a little bit, so I will pause the video and be right back. All right, it's done, so let's check it. So what you can see here is normal modes as a result, right? So you have just that for this analysis, and you can see here that you have the first 10 eigenfrequencies. And so pay attention to what is there here. One, you have the frequency. The frequency is one output, and that's the frequency where this eigenmode happens. The second one is the eigenmode itself, or the eigenshape, or however you would call that, is like the way the part deforms at that eigenfrequency. So basically, we can see now with eigenfrequency of around 60 Hertz, you see that you have motion at this side and at this side of the part. And because it's a lot easier to understand it if you just animate the structure. You could play the animation right here, and then you can see how it's jiggling, whatever. It's like shaking, yeah. And you could imagine that this would be somewhat of a weak mode of this part. Weak, I mean a low frequency, because the more stiffness you have, the higher the frequency it would be. Just imagine like the strings on a guitar. If you have the low E notes, it's a lot less torn than the high E note, for example, right? So stiffness and frequency is related. So that's one mode. You could also scale that up if you would like to. Let me quickly show where this is. Sorry, I cannot. Here. Is this a... Sorry, okay, this increment is just a playback speed, but I thought there should be a scale button. So this is the contour, but I don't see a scale button. But well, it's all right. You can see the motion here. If I find it, I will let you know in another video. All right, so this would be the first mode. So if you go to the second mode, you have another mode, which you could also imagine that this is a realistic mode. And you can also see like this bearing is moving in the Z direction, right? So you can see that it is working, and it's also turning a little bit, right? So you can see it's going here up and down. This point cannot move up and down, but as the rotation is free, it can turn or tilt. Yeah, and basically what you then do is you go through all those modes and see if there's something interesting to you. So basically the most important thing here is to check the frequencies itself and see that you don't have any frequencies like near that to avoid this excitement of the structure. So this is the first thing. The other thing you should then look for is if you have a shape and then maybe you have a collision problem. So if it's vibrating, but normally you would have some clearance to get that out of the way. But if you have really tight clearances, you should check that too. Okay, but basically that's about it for the normal modes analysis, how to set it up, how to run it. It's basically pretty easy, but what we also covered here is the connections or connectors with flexible and rigid, and also how to set this up. So basically that's that for the lecture. But there's another thing which I want to cover a little bit, and that's optimization here, because topography optimization is being used here, for example, to increase the lower frequencies. Why would you do that? Well, maybe you have a motor spinning at 60 Hertz here. And if you have that, you would maybe want to optimize your part that the lowest eigenfrequency is not 60 Hertz, but a little bit above that. And topography optimization is its own thing, which we cannot cover it here, but you will find also in the optional folder of this module, you will find something here. Let's just quickly make a new model and do this. You can see now like the structure here has been changed, and this increases the frequencies overall. And this is being used all over the place. You can see that, for example, on metal stair floors or something like that, or also every sheet metal in cars. You can see that. So this is being done in the industry quite often. So if you have a frequency problem, there should be a bell ringing in your head, screaming topography optimization, because that's a cool thing to do. You don't have to add too much mass, you just have to structure the part a little bit different, change the geometry, and then you're mostly fine. Yeah, so basically I will just pause the video here and do all the pre-processing here and just show you how the minimum frequency will look like. So I'll be back. Okay, that's done. So let's check it. So 60 Hertz was the original one, and now you see you have 86. Yeah, so basically, let me just quickly calculate that. 86 by 60, yeah, 40% increase. That's pretty big. For that I don't think you have too much of a mass difference, and that's really good. So what you can take from that is topography optimization whenever you have a problem with frequencies. You can do the normal modes frequency analysis here in Inspire, and for sure in industry context you would like to get a little bit more than just 10 nodes, modes, sorry, not nodes. And yeah, so we learned about connectors, we learned about material creation and assignment, and yeah, so if there's anything more you want to know about normal modes, please let a comment down, leave a comment down below, and I hope to see you in the next video. Until then, take care. Bye guys.